Hello, everybody. I appreciate it if you could turn your video on. Yeah. Hello, hello. So today's class is, I am Advay Misra, as you probably know. Today's class is going to be about two things. Firstly, so something called supersums of square weights, which is a cool inequality strategy, and another thing called Chinese inequality notation, which is a very nice way of noticing, like, an application of, say, Schur's inequality. So first off, give me one. So first off, what is supersums of square weights, or SOS? So the idea in SOS is that you write a sum. You write an inequality expression. Like, let's say you've got some h of A, B, C is greater than or equal to 0. So now the idea is that you write this as S sub A times B minus C whole square plus S sub B times C minus A whole square and S sub C times A minus B whole square is greater than or equal to 0. Now the good thing about writing it this way is that it's very easy to add different inequalities, and in particular we can add together two inequalities that are in different directions and measure which one is stronger. So for instance, just give me 1 moment. Am I screen sharing? Is my screen share active?
Yes, it's active.
Okay. You guys can see the board right now, right?
Yeah, we can see the mirror.
Okay, good. Thank you so much. Okay, so to take an example of why SOS is useful, consider that suppose we are trying to prove this thing. Um, a So like this is what we're trying to do. Now, if we expand out and like we will get something like this. So now the aim here is that we want to try to show that this inequality holds for like one cycle, or if you say it in that way, if you see it in that way. And so now in our aim to show this, we could write, say, but actually now in this case, this is a kind of annoying thing to try to do. So what we do instead is that we rewrite this as 1 by 3a by 4 plus b by plus b power 4 by 3. So now this is a very nice inequality to deal with. And over here also we replace a cube b plus c with a cube b plus a b cube. So now if we can do this two variable inequality, like, is that this is greater than or equal to a cube b plus a b cube, then we would be done, right? So now if we could say that we know that this holds, that if you take the fourth powers, then this is greater than or equal to half of this. Sorry, not half, I make 1/3 of this. And then for the other 2/3, we have this.
Can you show the problem once? I just joined.
Okay, yeah, so the problem we are discussing right now is to prove this thing.
Okay.
2 by 3a square plus b square plus c square whole square is greater than or equal to symmetric sum of a cube b. So right now we are looking at this two variable inequality. If this is true, then we can just cyclically sum this and we would get our desired inequality. So now this is true by by however you want to do it. Like, yeah, Moorhead works for this one. And now for this, Moorhead tells us that it holds the other way. So it looks like we are stuck. But what we can now do is that we can rewrite these inequalities in the form that 1/3 of a the idea is that we factor out a minus b whole squared from the whole inequality. In the latter case, that yields this. So this turned into this. And this yields that so are you guys with me so far?
Yes.
All right. So now what happens if we just completely, if we ignore the fact that these two point different ways and just sum these two, we get this. And we know that this is non-negative, which, and because this is the sum of two things that originally summed to this, we know that this inequality also holds true because it's just this top inequality uh, written in a different way. So we are done. So this showed the power of SOS in that we can add together two inequalities in different directions and get an expression, and we can talk about whether that expression is positive or negative. Another useful factor that is very important for SOS is that suppose I have a polynomial in two variables. In that case, if the polynomial is symmetric, and it has a 0 at a equal to b, then a minus b whole squared divides p of a comma b. So that is to say, a is equal to b is not just a root, but also a double root of p. So this is really useful for SOS because because essentially a very common strategy we will apply when using SOS is that we will take an expression, which is usually some form of cyclic sum, write it as a cyclic sum of a different polynomial which satisfies these two things, and then we apply this and get SOS. Now in SOS, so these three weights. So now if SA, SB, SC are all greater than or equal to 0, then obviously this thing is non-negative. But in fact, we actually have even better results than this, because even if SA, SB, and SC are not all non-negative, then we can still use alternatives. So for instance, SA, SC if all four of these are non-negative, then we are done. Then another thing that we have is that if So if you take B to be the median, then SA plus SB, 0 plus SB, and SC plus SB are all non-negative, then that's also enough to conclude. Then if A is greater than or equal to B is greater than or equal to C, so not only is B the median but also C is the least, in that case then then it's enough to take the two smaller, and then this interesting sum. So this is one criterion, this is one criterion, this is one criterion, and this is one criterion. So if any, so these four are pretty useful. Does everybody understand these four criteria? One month.
Could you re-explain?
So the idea is that in SOS we can write the inequality as a sum of these three things, and we have to show that this sum is non-negative. Okay, is that sensible?
Right.
So now we have a bunch of conditions on these three weights, that if any condition holds, then we are done.
Okay.
So the simplest is that all are non-negative. If all four of these are non-negative, then we're also done. If all three of these are non-negative, then we are done. If all three of these are non-negative, then we are also done.
I see. Okay.
Okay, so now let's talk about Chinese notation. So the idea in Chinese notation is that you set up a triangle like this with the highest powers of A in the first row, then the second highest in the second row, the third highest in the third row, the fourth highest in the fourth row, and so on. And then similarly you arrange the powers of B and the powers of C along the diagonals. And so you can fit all the possible terms of degree 2 or of degree 3 or of arbitrary degree onto a triangle like this. So this notation is really useful for representing a homogenized inequality, or to be precise, a homogenized expression. So here are a couple examples. This represents that this is a plus b plus c whole squared. So you can see this is a squared, 2ab, 2ac, 2bc, b squared, c squared. Does this example make sense?
This is kind of like Barry, right?
Yes, a very good analogy. You could see the system as being based on barycentric coordinates with the point with like a power x, b power y, c power z being at barycentric coordinates x, y, z. Yes, that's a good analogy. So this is a couple of common inequalities represented on a degree 3 triangle. So this is Schur's inequality with degree 3, and this is AMGM on 3 variables. In general, AMGM looks like you have a bunch of points.
Could you show the original problem that you did first in class?
For SOS,
Yeah.
this one.
Okay. Thanks.
Yeah. Also, if at any point you feel that I am going really slow and you want something to, and if you get bored and want something to do, then you can just note down this problem and try it, I guess.
Excuse me. I just had Sure, that's fine.
What's your question?
Like for the four, like what do you call it? The weights that you talked about, the four options.
Yeah.
Is it like double implied? Like by that I mean, if the inequality is true, then one of them have to be true, and if one of them is true, then the inequality is true.
If any of these are true, then the inequality is true, but it's not necessary that a true inequality will satisfy one of these four criteria.
Okay, got it. Thank you.
You're welcome. Okay, so if anybody else has any questions, feel free to interrupt me and ask. Okay, so in general, AMGM on n like points somewhere in the triangle will look like you have a bunch of points, and each of them has like 1, and their center has coefficient -n. So like in this case, the center has coefficient -3, and the 3 on the outside have coefficient 1. So now for a demonstration, okay, wait. So first, um, you can actually, so the cool thing about Chinese notation is that you can use it to multiply with things reasonably well. So let's say you're multiplying these two things. So this is, so do you so what is this representing? Like this is known to be greater than or equal to 0. Um, does anybody know what this inequality is?
Is that just Schur's inequality?
Yes, that this is Schur's inequality on degree 3.
Wait, what is Schur's inequality statement?
Schur's inequality can be stated like this. Yeah, this is Schur's inequality.
Okay, and what are the conditions on ABCR?
So basically A, B, C are themselves non-negative. Then
Okay,
this.
thanks.
So if you set R to 1, then you get this triangle. And this is just A square plus B square plus C square. So now to multiply this, because it's degree 5, let's take a degree 5 triangle, which has side length 6. So the idea is, so the way that you do the multiplication is that you match up this one with this one with this and with this, and then you take this and you multiply it by 1 and you copy it over there. So like this will have 1, 1, 1, 0, 0, 0. Then this -1, you match it with this, multiply, so this, and then you place that over here. So -1, 0, 0, 0, -1, -1. Since in the end we're going to be summing anyways, you can just omit any zeros. So then this one minus 1, minus 1, minus 1. Then this one minus 1. And then this 3. And then finally you have okay. So do you understand how we got this?
Yeah.
Yes?
Yeah.
Alright, good. And now we just sum up all the entries in each box. So like these two will cancel out. From now on, I'm just going to leave zeros blank because because a lot of inequalities with a few terms will have zeros everywhere, and it's really annoying to write them all out. So we get this, and we just saw that. So now this is the product of these two expressions. And we know that these two expressions are both non-negative. So we know that this is non-negative. But if we didn't know that this was the product of those two expressions, then it is a little difficult to spot, right? That it is that product.
So
So
basically, the numbers over here represent the degree.
the numbers
How?
over here are the idea is that you write out all the possible terms in a triangle like this. So like this is for degree 3.
Yeah.
So all the terms where it's a cube, that gets the topmost row, then a squared, a, and then a power null.
Yeah. Okay.
And then you have the same thing along b and c for the diagonals.
Oh, okay.
And so like this represents a cube. This is minus a square b minus a square c minus ab cube plus abc minus ac squared, sorry, plus 3abc minus ac squared plus b cubed minus b square c minus bc squared plus c cubed. And this is greater than or equal to 0 by, that's what Schur's inequality says.
Yeah. Okay. Okay. Got it. Thank you.
Alright, good. So now let's try and prove that this is non-negative by writing it as a sum of stuff. So the first thing is that, okay, so Schur's inequality when written like this will end up looking like uh, so Schur's inequality is essentially like this. It has this like distinctive shape of 1, -1, -1, 1, and these lozenges are positioned in the three corners. So we can write that inequality as the sum of this plus in so now the idea is, so what we're trying to do here is we're trying to show that this is non-negative by writing it as a sum of non-negative things. So we get this, and it would be enough to show that this is non-negative. So can you get? So do you recognize why this is non-negative?
AMGM?
Sure, yeah, that would work. In fact, this is actually just this cyclic sum. This is a very acrobatic summation sign. And this is, yeah, this is AMGM on two variables, but it's also just a minus b squared multiplied by some factor. Sorry, b minus c squared in this case, multiplied by some factor. So yeah, so that's a simple example. So now let's take our first example problem. This is the problem. Okay, so try this problem out for a couple minutes. How long do you guys want to try for? Does anybody have any opinions?
5-10 minutes would be nice.
All right, so try this for a moment. Also, just to be clear, you do not have to write these circles when doing Chinese inequality notation. It's just for my convenience. Yes. Okay, so it looks like some people have got the solution. So yeah, so this one, yes, there is a very nice. So it's very easy to just do AMGM on the H square and get that this is greater than 3ABC, this is greater than 3ABC, and in this case, though, we can actually solve the inequality without doing basically no computation. In fact, literally no computation, aside from like 3 1 sum to 3. So this is so you get this hexagon, and then you can subtract the 9 ABC to get that we want to prove this greater than or equal to 0, and this is just AMGM. Remember these 6 points, and in the center is a -6. So yeah, so this was a pretty nice simple problem. Okay, so next up is a very good problem for demonstrating how Chinese notation helps us spot inequalities. So try this until I guess 542, and I'll check back in there.
Excuse me.
Hello.
Is it possible for you to re-explain the multiplication process?
Okay, so the idea with the multiplication. Okay, let's take the example from. Oh yeah, I deleted that. So I'll just take the example I already have. So let's say we're doing this multiplication. So what we do is that we take this. So we basically identify this part of our first multiplicator, first term, which we identify with this. Okay, and then we take this and multiply it by the, and then we go through each like term over here. So let's start with 1. So you multiply this thing by 1, and then you install it at, and then you put a copy of it where at the relevant place. In this case, we have 1. Then we aren't writing the zeros because in the end we will sum them up anyways. And 1 and 1. So you can see that these 3 ones correspond to this 1 multiplied by this. Then this -1 corresponds to these 3 negative ones. This 3 corresponds to these 3 3s. So you get this triangle with a bunch, and then you just sum up all the numbers within each circle over here. In practice, by the way, just to be clear, you don't need to always draw the circles with Chinese notation. It's just I'm just doing it because it's more convenient than drawing 42 circles by multiple times. So so you get this. Right now I'm leaving the 0 cells blank. So you understand. So like this, these two negative ones combine into this -2. So does that make sense?
Correct. Thank you.
All right, good.
Your voice level was fluctuating, so could you keep the mic near you?
Hold on. Is this better?
Yeah.
All right, good. All right. So has anybody solved this problem yet? All right. So, does anybody have any thoughts at all about the problem? Okay. Yeah, so the first thing to do here is to just homogenize the thing. So, if at any point you feel that the class is going too fast or too slow, then please feel free to say so. So we've homogenized the inequality to degree 0. Uh, so now we can just rewrite this as a bit. Note that because of this earlier 3ABC, we actually can just get rid of all the factors of 3.
I had a question. Uh, like, is the claim that the minimum value is 0 or?
Sorry, yeah. So okay, yeah. So about that, so mm, yeah, sorry about that. I was referencing an earlier version of my notes in which I had originally had the problem be greater than or equal to 0. So the reason we can guess that the minimal value is 0 is that it it's like all the terms are of negative degree. So having particularly large values would make, so if you have a really small value, then that's going to make a pretty big like impression. And also because it's just simpler to consider degree 0. Sorry, okay, hold on just a second. Yeah, so if you set A equal to B equal to C, Yes, also thank you to the person who pointed out who pointed this out. So so let's say that this is greater than or equal to k. Then we get that rearranging everything. This is what the inequality is. Okay. Yeah, so does everybody agree with this so far? That it's enough, if we are claiming k to be the minimal value, then it's enough to show this. Uh, does anybody want to say anything? Like yes or a no?
I have just one question.
Yeah.
Yeah, what do you mean by homogenize? Like, not sure. How do
Uh,
you?
so the idea of homogenizing is that you try to get all the terms to be of the same degree. Like if you sum up the degree of A and the degree of B and degree of C in a given term, all of those should sum to the same thing for all the terms in your inequality. The reason that it's useful to homogenize is that it usually lets us get rid of conditions like this. Because
Uh,
because if you have your inequality homogenized, then you can scale A, B, C arbitrarily, and so so you get that if it's true for this A plus B plus C equal to 3, then it should be true for A plus B plus C equal to anything non-negative.
okay, got it. Yeah. So basically, we want to maximize A, B, and C, right? So that we can have a minimum value of this expression.
But uh, remember that, okay, so looking at the homogenized version, having a very small, so having big values. Okay, so here's one way to think about it. If you try to make a large value for A or B or C here, then because all of these are inverted, then you will get everything is like everything occurs in a denominator somewhere. So
Yeah.
if you make A big, then you have to make B and C smaller.
Yes, that's true. Yeah.
So in fact, it turns out that the best you can do is by setting A, B, C all equal.
One, right?
Yeah.
Yeah.
But
Okay.
because the inequality is homogenized in this case now, every term is of degree 0 when you combine A, B, and C.
Okay.
You it is so that works out. So that case is equivalent to saying k is equal to 1 with reference to this, where
Yes.
we said k is the minimal value. So now so we can check this case. If it turns out to be wrong, then we won't have wasted too much time because this term cancelling out will save us a lot of algebra. So what we're left with now is this. So we are trying to prove this. If this turns out to be wrong, we'll go back and try to find a better value for k. Yeah, sorry about my bad handwriting. Okay, so do you understand why we are trying k equal to 1 for now? Um, hello, if anybody wants to give an answer to the question, then it's fine. Okay, so looking at this, what do you think we should do now? We're looking at this case. What is something we can do?
Maybe we could square both sides.
Okay, yeah, that's a good idea. So I'm just going to skim past the. So in order to do the square, you can basically just write this. And you can evaluate this with not too much difficulty to get. And we're basically claiming that this is greater than or equal to 4. Got it? So does it make sense? Do you understand how we were able to derive this inequality? Yes? Hello?
Yes. So can we now like shift the
Shift the what?
denominator terms?
How?
Maybe by taking LCM or something like that.
Oh, okay. I mean, since we have this ABC over here, and so we see a bunch of a squares in the denominators, so we could try multiplying by a square b square c throughout to get, sorry, a square b square c square. Okay, so now we get this inequality to look at. All right. Is everybody following? Guys?
Yeah.
All right, good. So now if we move everything over to the same side, then it basically just becomes this. We have to prove this non-negative. So it is time for the triangle. Let me just grab one. Okay, so first let's write out this thing in the symmetric sum. So A4C2 will go over here. A2 minus 2A cube B square C. A power 4BC plus B cube C cube. A square B square C. Now, in order to get the symmetric sum of this, the idea is actually quite simple. So first of all, you just take this and multiply it by its mirror image. Sorry, don't multiply it by its mirror image, add it to its mirror image, which corresponds to the terms of the symmetric sum. That are which swap B and C. So is everybody following along so far?
Yeah.
And then you just take this and add on the rotations, which are the other symmetries. Yeah. So adding up, you get this. So now we have to prove that this is greater than or equal to 0. Okay? And now we can see why this notation is so powerful. Can anybody recognize an inequality in here? In this triangle, can you spot a particular famous? Remember that if you have that a given thing is non-negative, you can like move it around in a sense. So like, for instance, this 1, -2, 1 along the bottom is definitely non-negative. So does anybody have any ideas on something you could see based off of this? In fact, I've already shown you the diagram for this inequality. Yes, this is 2. My bad. Thank you, Avdhu. Yes, Krishika is correct. We can make sure it's very difficult to see without the triangle, but this is Scher's inequality, degree 3. Yes, and also upside down, which is why this notation is particularly useful. And then the 1 minus 2 minus 1 along each side is just AMGM. So we're done. Yay.
Just one question again.
Correct.
So wait, why can't it like get below 1 again? Like
What can't get below 1?
like the minimum value for that.
We just so the idea was that we just like guessed that the minimum value was 1 because that simplifies the algebra. So it wouldn't be too much. So we wouldn't have lost too much time on that, basically.
Okay. Got it. So
Yeah.
so like we can't like go below 1. Like have we shown that we can't go below 1?
That's what we just showed, right? That if the value is less, we showed that if you set k to 1, then it's enough to prove this. This is equivalent to that this expression is greater than or equal to 1 is equivalent to this.
Okay. Yeah, okay. Got it. Thank you.
Yeah. And then we proved that inequality by upside down Scher's inequality. Oh yeah, so yeah, that's
Wait, I'm really sorry, but I still didn't like get one thing.
Yeah.
Like how does that imply like greater than one is not possible?
Greater than 1 is definitely possible. The question asks for what is the
I'm sorry,
minimum.
less than.
Less than 1, because like, so basically you've got this. So this is the inequality we're trying to show. Ignore the decapitated fractions. And that inequality is equivalent to this inequality by just like moving stuff around. Got it? Like this inequality, right? Does that make sense?
Yeah.
And then this inequality, we manipulated into this inequality, which we then triangulated into this, and then we wrote this triangle as as a Scher's inequality plus 3 AMGM inequalities.
Okay, got it. Thank you.
You're welcome. Okay, so time for another problem. Uh, okay, let's do this one.
Is there any other way to do the last problem like without using this thing?
This one,
Yeah,
without using what?
like without using the method we're using it.
Without using the notation. So is that what you're asking?
I guess.
Yeah, so if you want to solve this without using the notation, basically you just, you'll get this. And then if you look at this for long enough, you'll notice basically this Scher's over here is equivalent to, just a sec. So you have, so on the outside, you just, so these two, so these AMGMs basically are, so you have, if I click sum of A4, B minus C squared, that corresponds to this AMGM and like its cousins on the sides, plus Scher's inequality on AB BC and CA. Yay. So like basically all that the notation does is that it helps us see the inequalities in a sense. So like over here, it's not particularly easy to spot the Scher's inequality on the ABBCCA, but with the triangle, it jumps out at us with this distinctive pattern. Okay, so does anybody have any other questions, or shall we move to the next problem? By the way, yeah, so now the idea, okay, let me see which problem to do. Okay, so Let's take this one. All right. So now, what is your first instinct with this problem?
Can we just expand?
That's it. That's it. Yeah, that's the thing. So you basically get this, I believe.
Get two 6-degree polynomials.
Yeah. Can you tell which those are? Or we can just calculate them again.
Yeah.
Let's just calculate them. It's this. Right? Yeah. So because it will be really boring to just go through all of this manipulation, even if the Chinese notation can help us through some of the algebra, I'm just going to directly tell you what the polynomials are. Okay, why don't we just do this actually? So let's see over. So the first thing to do is evaluate this product because we're going to need it twice. So let's do this. So it's just this, right? Or actually, let's take this version because it's a bit more symmetric in a sense. The symmetry is horizontal instead of an annoying diagonal. So just gonna grab a quick triangle. So the result is degree 4. And so let's do the multiplication. It's quite a nice pattern. Looks kind of like a square with your 2's at the midpoints and 4 in the center. And now we are multiplying this by two different, also second degree things. One of them is this, and the other is this. So you get so for the left hand side will be 4 times this first product, which looks like Okay, so just one. We note that we can use the fact that this row and this row are pretty much the same to say that this row and this row will be almost the same. So it's 4 times this, and the other addend is where did I do that? Oh, wait, no, this is actually the left hand side. So yeah, this is the right hand side because we multiplied it by the last remaining square. This is the right hand side, and this is the left hand side. Or to be precise, this is one of the things that symmetrically sums up to the left hand side.
Sorry, but I just had a question here.
Yeah,
So like over here, like isn't it like a degree 6 thing? Like why
yeah.
are there? Yeah, but this one has only like degree 5. This triangle.
Mm. Okay, so you see, we are currently looking. So the highest power of A, that there is no like. So what we're currently evaluating this product here, and uh, because actually that's a good point. Something I think I messed something up.
I think like when you copy pasted it,
Oh yeah,
you
yeah,
have to be
yeah, I
on the
realized my mistake. Yes, it was supposed to be this. Thank you so much for pointing that out. That was very helpful of you. Yes, thank you so much. Thank you so much. Yes, so this is what, so this is the right, and this is the left hand side, and this is the right hand side. So I'm doing the relevant subtraction. Oops. Wait, yeah, I just have good. So, okay, so this is the degree 6 triangle. So we are basically just computing 4 times this minus 9 times this. So the corners are all just 0. Then this, wait, yeah, sorry, I forgot about one thing. Yeah, so we're just going to put this onto the thing right now because we still need to do the sum, like the cyclic sum. Another good thing is that about the Chinese notation is that you can like very easily see that it is that this is like symmetric in B and C because swapping B and because yeah, it has this vertical line of symmetry. So I'm just going to
513.8 looks like Fibonacci.
yes, that is interesting actually. I wonder if this is some if there is some connection to the Fibonacci numbers. Yes, all the numbers here are Fibonacci numbers, which is interesting. Oh, wait, unfortunately, actually, no, because this
7
8.
is not Fibonacci.
Hmm? What?
17 is not Fibonacci.
But there is no 17. These
Oh,
are
13. Oh, okay, okay. I thought it was a 17.
no. See, it's it's
Okay.
symmetric. So
Yeah.
like, yeah. Unfortunately, I don't. Yeah, 24 isn't quite Fibonacci either. So maybe that was just a fluke. But let's. Okay, yeah. So it's 4 times this minus 9 times this. So now for the subtraction, I'm just going to. Yeah. So you get. So the it's useful that both of these are like symmetric in ABC. So like you can swap. So if you see, they have this vertical symmetry and they also have rotational symmetry. So that means that like once I compute that this is going to have a 4, all of these guys are going to have 4s. And then 8 minus 9 negative 1. Then 12 minus 18 negative 6. Then 52 minus 54. Okay. All right. So, looking at this, what are your first impressions? Anybody have anything to say about this? Oh wait, yeah, this is negative 2. My arithmetic skills are a little, yeah, so, yes, so this is correct. So, looking at this triangle, what do you see? What jumps out?
Could we like use like Shah's again on that triangle? Like not entirely, like it's not like fully compatible. But like could we like subtract it out or something?
Hmm?
I don't know. That was just
Okay, so let's see. So, what would so shares would look like? So using so do you okay yeah so shares in so isolating shares inequality. Never mind, you cannot actually use that to illustrate.
Oh, I didn't see that.
Then along the sides, do you recognize this pattern? Wait, actually, never mind. So now for this middle part, I think I missed something. No, I haven't. So now we are left with a very interesting two variable inequality, which is basically this. So you get this, and does anybody have any guesses on how you might go about proving this one?
Wait, isn't it minus 6a squared b squared?
Yes, it is. Sorry, that was a mistake. Actually, I was consider so. Okay, yeah, no spoilers. So try this thing for a while. If we do this, then we are done, right? Because we can just add that to Schur's, and then because this is basic, this triangle being non-negative is equivalent to our original inequality, we'd be done. So anybody got any ideas for this thing? We want to show this is greater than or equal to 0. So any ideas? Remember that lemma I mentioned when we were doing SOS, that if I have a polynomial, let me just go back to the main area, which is where okay, yeah, this is the. So when we were discussing SOS, I mentioned this lemma that if you have a two variable polynomial which is symmetric and uh, also has a root at a equals b, then it has a double root at a equals b. So we can actually use this on this inequality because it's symmetric in a and b, and if a is equal to b, then it zeroes out 4 minus 1 minus 6 minus 1 4.
When then after that, it's like a quadratic being more than 0, which is easy.
Yeah, and that's it. It's we. So again, the power of the triangle notation is twofold here. One, it made the multiplications really easy. We never forgot a term or anything. Although I did almost mess up one multiplication, but I should have got my mistake. And then in the end, we were able to, is this sure in the middle, jumped out at us. This is a really big advantage of SOS. The important inequalities like jump out at you. Sorry, of not of SOS, of Chinese inequality notation. So going back, okay, so uh, okay, so originally I was going to do this as the next problem, but this is a long and not particularly insightful problem, so I'll go with this one instead. So this one is pretty short. So yeah, just I don't think you even need the triangle for this one. You can just do it directly. So like, actually I'm just going to write it out. AQ plus BQ plus CQ plus 6ABC is greater than or equal. And now it's just a matter of, now let's put it on the triangle for good measure. So just compute this, and you'll see why I chose this as the problem I'm probably going to end the class on. Has anybody done it? Is anybody doing it?
Is it just Shah's again?
Yes, it is. This works out to 3 minus 3 minus 318 minus 3 minus 3 minus 3 minus 3 3 3, which is more than thrice Schur's inequality on 3 variables. But it is known to be non-negative. So yeah, that's all, folks. So going back to the problem select menu. So just, I guess, take a screenshot, or you can go to the recording and try out these problems. Yeah, these are So these problems are based off of what I did today.
Get these from?
Various places.
Okay.
And mostly just scrolling through AOPS. And a few are from handout I have. So then this problem isn't based off. This problem is unrelated to what we did today, but I think it's just pretty cool.
Isn't that Vasquez inequality?
Yes, this is Vasquez inequality.
Okay.
Yeah, and then another one which I like is that so for a polynomial p, consider. Hold on. Consider this thing. Okay. If this holds for x equals 1, then show that it holds for all x.
Is P an integer polynomial or?
P is a polynomial with positive coefficients.
Oh, okay. Got it.
I probably should have mentioned that. Yeah. So try these two out as well.
So it holds for 1, right?
Yeah, it holds for 1. Show that it holds for all x.
Okay.
So these two are just two cool inequality questions, not related to what I did today. I showed you a couple more problems to try. So yeah, try these out, and I'll see you next time. Thank you all so much for attending.
Thank you.
Thank you.